Hello there, students. In this video, we're going to be talking about the most common acceleration in physics, gravity. In this discussion, we're not going to consider air resistance or any other effects since we haven't formally introduced those topics yet. Near the surface of the Earth, the gravitational acceleration, g, is near constant and has a magnitude of approximately 9.81 meters per second squared. We know that acceleration is a vector, thus it must have a direction in addition to this magnitude. From your own observations and intuition, you can probably conclude that the direction is down, or toward the center of the Earth. Our choice of coordinate system will dictate if that direction is positive or negative. Since we are still in one-dimensional kinematics, we restrict objects in motion affected by gravity to only move in one coordinate or dimension, either up or down. In previous videos, we've used the x variable when objects were in motion, but to be more consistent with future lessons, we will change the variable for the direction of motion for objects affected by gravitational acceleration to the y coordinate. This is reflected in our kinematic equations like this. When an object is thrown upwards and is affected by gravity, it will slow down until it momentarily stops at the highest point of its trajectory. At that exact moment, the velocity in the y direction is exactly zero. A moment later, gravity will continue acting on the object, accelerating it back down. Let's try a quick example to see this. If you threw a ball straight up with an initial velocity of 15 meters per second, how long does it take to reach the top of its trajectory? We can use this kinematic equation, since we know the initial velocity, and we know that the final velocity at the top of the trajectory will be zero. The acceleration is from gravity, and we pick up a minus sign on the acceleration due to our coordinate system. Solving for time t and plugging in our values, we find that it takes t equals 1.53 seconds to reach the top. Now we can also ask, how far has the ball traveled when it reaches the top of that trajectory? We can let the initial throwing position be y0 equals 0 meters. We also know that the velocity will be equal to 0 at the top, so v sub f equals 0. Then we can use either of these kinematic equations to solve for the final position. Using the first one, we find a final y position of 11.47 meters. Using the second equation, we also find a final y position of 11.47 meters. To help understand this motion, let's look at some graphs of its position, velocity, and acceleration over time. Here, we see the ball starts at an initial position of 0, has a positive initial velocity, and a negative acceleration due to gravity, all at time 0. The ball moves in the positive y direction for a time, before reaching its apex, its topmost point. At that point in time, the velocity is 0. Afterwards, as the gravitational acceleration remains constantly negative, the velocity becomes negative and the ball begins to descend. Instead of throwing the ball upwards, what if you were standing on a bridge and dropped the ball towards the water, 100 meters below the bridge? How long would it take to hit the water? We can solve this with this kinematic equation. In this case, we need to be careful with our coordinate directions and make sure that we apply the correct signs to our final y position and gravitational acceleration. First, let's choose the standard coordinate direction of up to be positive. This makes the final y position a negative 100 meters and the gravitational acceleration a negative 9.81 meters per second squared. We also know that we are dropping the ball and not throwing it, so we are not giving it any initial velocity. Said another way, when we drop something, its initial velocity is equal to 0. Solving the equation, we find that it will take 4.52 seconds to hit the water. We take the positive result because a negative time doesn't mean anything to us here. We could also ask, at what speed does the ball hit the water? To answer this, we can use another kinematic equation. Again, being careful with our coordinate directions and negative signs, we get a final velocity of plus or minus 44.3 meters per second. Since we were just asked for a speed, we only need to report the magnitude of 44.3 meters per second. If we were asked for the final velocity, then we need to think about which sign to take as our answer, since the sign gives us a direction and makes our answer a vector, as is required for velocities. Intuitively, we know the object is falling, since we've chosen up as our positive y direction and the ball is moving in the negative y direction. That tells us the sign we must choose is the negative one to reflect that the final velocity is in the negative coordinate direction. We can once again take a look at this motion on our graphs. As a last exercise, consider you were standing on that bridge with a friend. You throw your ball straight up into the air with an initial velocity of v0 is equal to 15 meters per second, and then let it continue on its way to fall into the water, which is 100 meters below the bridge. Your friend throws their rock straight down towards the water below with an initial velocity of 15 meters per second also. Which rock will hit the water with a larger final velocity? Pause the video, ponder for a moment, maybe work it out on a piece of paper. Welcome back. So, did you think your ball that was initially thrown upwards would have a larger velocity on impact, or your friend who threw it straight down towards the water? It turns out that they will both impact with the exact same final velocity. We can check this by using our kinematic equations. Let's start by calculating the final velocity of your ball. Let the bridge be a height of y0 equals 0 meters. The ball then ends its trajectory in the river, a final position of negative 100 meters. Your ball was initially thrown upwards with an initial velocity of 15 meters per second. We can use this kinematic equation, where the total displacement is negative 100 meters. This gives us a final velocity on impact of plus or minus 46.8 meters per second. We choose the negative one because we know that the velocity is in the negative coordinate direction. Now we can use the same kinematic equation for your friend's ball, this time with a negative initial velocity. We see that we're going to square this initial velocity, so the negative sign really didn't matter, and all the other components are the exact same: a vertical displacement of negative 100 meters and the same gravitational acceleration. Thus, we get the same final velocity of plus or minus 46.8 meters per second, and again we take the negative one. Now, even though they will both impact with the same final velocity, your friend's ball, since it was thrown straight down, will certainly hit the water in a much shorter time than yours, but that wasn't what was asked. In the next video, we'll leave behind one-dimensional kinematics and start looking at motion in 2 dimensions with projectile motion. Thanks for watching and learning about physics. If you have any questions, please leave a comment on the video or head over to my Facebook page in the video description.